d copies of a random variable which is normalized to have mean 0 and variance 1. Okay. I will mainly talk about the real case, the result applied in the complex case, but I will not mention it. Okay. And two examples you can easily think about is the real Gaussian random matrix. If you are a probabilist, or if you are a combinatorist, then you can think of plus minus 1 matrix. Every entry is the fair coefficient. Okay.
You don't assume these matrices are Hermitian or symmetric, right?
No, we don't assume symmetric. Yeah, symmetric. The result also sort of hold in the symmetric, but it requires a different technique that I would not talk about here. Okay. So actually, in this case, we know that the eigenvalues can be complex, but if you do linear algebra, the thing that really matters is the singular value, which are real and actually non-negative, and I denote them decreasingly sigma 1 to sigma n. And this sort of tell you how the matrix as an operator change the space. So you know that the operator M as a linear operator from Rn to itself will mappable to an ellipsoid. Right. Say assume that we take a unit ball, and the ellipsoid will be very long in some direction and very short in some other. And the longest direction here is actually represented by the value of sigma 1. It's the largest singular value, and the shortest direction is sigma n. Right. So yeah, the longer this ellipsoid is, the worse the matrix sort of distort the space. Right. And the condition number tell you that how much it distorts the space. If the condition number is 1, then actually this map is just an identity map. It's mappable onto itself. So it tells you that how distances is changed in the map. And it is of fundamental importance in numerical linear algebra and anything that anything that related to linear algebra as linear programming. For instance, if you just take the basic equation mx equal to b, I just copy it from a numerical algebra book by Trevercan. Then we know that the exact solution, okay, let's assume that M is invertible. Then in theory, we can invert the matrix quite easily. Right? There's no problem about it. In practice, that the books say that the computer has, it represents only a subset of real numbers. You cannot have all the real numbers there. We have only a finite number to work with, and so there are gaps between these numbers that the computer used. And a quantity that matters here is that how big the gap, and so they normalize it by say taking half the gap from 1 to the nearest number that the computer can use, which is denoted by epsilon machine, which is some standard notation in that area. And now if we talk about the solution x, of course it will be changed to some x tilde, and the arrow here is actually the relative arrow is going to be proportional to epsilon machine, which is of course what you expect, and it is also proportional to the condition number of the matrix. And you can find the matrix. You can find the proof in that book. It's like 1 or 2 pages long. Just take it as.
For integer matrices, you can compute with infinite precision if you want.
Yeah. So yeah, it is just example to make a motivation. It's not something to be discussed in great details or anything. Okay, so the problem was raised in very early, even before, it was the time when computer was began to be built. Goldstine and von-Neumann in the 1940s. And actually, I think they discussed it in here, both of them in the institute at the time. Maybe not this building, but so, well, they could have stand here as
I believe they were actually at the Crossroads building.
yeah, but they did try to build the computer at that time, and they wrote I think a series of 5 or 6 papers about what have become later on of numerical analysis. And so one of the paper is entirely about what is a condition number of random matrix. And I will not prove anything about this, but it is fairly well known that in the ratio between sigma 1 and sigma n, sigma 1 is quite well understood, and it is basically of order square root n. It's roughly 2 times square root n. So the question is about to estimate the smallest singular value. So the flatness of this ellipsoid. Yeah, that's why the title is about singular value, not about the condition matrix. And in that paper, they make this prediction that this will be of order of 1 over square root n. They even try some explicit formula but did not succeed, and because of this, then this thing will be of order n. And yeah, they actually they make a lot of calculation, numerical calculation to figure out the law there, and I've learned later on that.
What's their model for random matrices?
What?
Which random matrix did they
Yeah,
consider?
this non-symmetric. They take Gaussian. They take Gaussian one. But the numerical, I think they probably make the numerical with plus minus 1 as well, because Gaussian one is hard to generate by hand at least. And I gave this talk in New York some time ago, and people told me actually these numerical are very hard, very costly to make it in that day, because they need like 100 people just computing all this stuff like day by day. There's no computer there. Even you do something with like 50 by 50 matrices, it takes a long time.
I thought von Neumann could do all these things.
I think he can do 5 by 5, but okay, yeah. And later on, the problem, the same question surfaced in later study by Smale and Demmel, and they talk about typical complexity of a numerical problem. And so this probably it is more like a nowadays language that you talk about complexity of the average case. Okay, another thing in the title that the talk I mentioned is a more recent work of Spielman and Teng in early 2000. Well, it gets a lot of mentioning lately, of course. Is a smooth analysis of linear programming. So we have this problem that we have to maximize the goal function c times c dot x and condition on ax less equal to b. Right? So basically, you have to find the point, the highest point in an polytope, say. And the simplex method is widely used. It is proved to be exponential in the worst case, but usually it's run very fast and people still keep using it. And Spielman and Teng have a great success in explaining this phenomenon. And what the explanation they come up with is involve randomness, namely that they argue that basically you will not work with this matrix A, never, but because of random noise, you will work with a perturbation of it, a random perturbation of it. And what they prove is that with high probability and Gaussian random noise, the algorithm, well, a certain implement of the simplex algorithm will run fast with high probability. Okay. And the main mathematical question, if you read the ICM paper by Spielman and Teng back in 2002, it is that you need to prove that with high probability this randomly perturbed matrix have a small condition number. So it is a nice matrix in some sense. Even when A itself can be very bad. It can be even a flat, say like sigma 1 can be 0, for instance. But Mn is actually, I like this because the philosophy is that actually the noise helps in some sense here. It's not a negative thing. Okay. Okay, so we have two problems. So the one problem is that the matrix A is 0, that is the base problem in random matrix theory, and the Spielman-Teng is that we can take any A. Okay, so as I, if we take about the base case, when A is 0, we just talk about the matrix itself, then in the Gaussian case, the problem is solved. And it is solved for all the other, most problem for the Gaussian case is solved because of the fact that we have the joy distribution formula for the singular value, or for the eigenvalues of Mn times Mn star, which is a square of the singular value. Right. So this is some formula that you don't need to care about, and in order to answer the question, we just have to compute some explicit integration on this, which is doable. It's not easy, but doable by.
So this formula doesn't sort the eigenvalues in order. It's symmetric in all the lambda.
No, it doesn't. Yeah. So it's tricky to compute the least singular value. It was first done by Elderman in '88, and he did both cases. Real Gaussian and complex Gaussian, and it gives you some formula, actually quite nice. I just wanted to tell you one interesting thing is that in the real case you have an arrow term, the factor n here is of course a normalization, because we know that this guy have order 1 over square root n, right? So we need to multiply with square root n and square everything. Actually, in the complex case, it's exact. It's quite somehow quite interesting. I don't know how to explain it because I don't know this integration technique. Yeah. So he used something called the trichotomy functions.
What are trichotomy functions?
I don't know. That is just like you have this function, you plug it there and it pop out. And all this in like 3 pages. And there's a lot of integration like this. And okay, so more recent work, I think more systematic, but this is not very readable here. You can also compute the joy distribution of not the smallest singular value, but say the joy distribution of say the smallest 3 singular value. But again, the answer looks much worse. And then the best cell kernel coming in, this is more systematic study. Okay, the main disadvantage of the integration method is that it relies on the formula that you integrate upon, and then you can do nothing else for the other distributions. Okay, so now let me jump to the Spielman-Teng analysis when A is not 0. So I will denote An by A plus Mn, which is the core matrix plus the perturbation, the noise. Okay. So what they prove also together with Sankar is the following. Assume the noise to be Gaussian, and then look at this perturbed matrix. Then the probability that I think it's not the condition number, it is the least singular value. It's probably so. Yeah, it's the least singular value. It should be sigma n. Yeah, apologize for this. Yeah. I was confused between the two notions. Yes, I make up the title. Yeah, so the probability. So here you can see that sigma n is also of order 1 over square root n, basically, because to make the right hand side to be a constant, then you have to take t to be 1 over square root n. And then and this is true for any t. You can take t to be 1 over n to the 100 or e to the minus n and so on.
So C is a universal constant?
Yeah, c is 100, say. Yeah. Actually, they computed like 2.5. And they also have like conjecture what is best value. Yeah, it is reasonable constant, not only.
Is the reason why that's true is if you look at the ellipse picture, then presumably the smallest dimension depends only on m, not really on a. Right? A has really bad condition.
Probably the worst conjecture. The worst C is when, because here you can imagine something like you shift a ball, right? And look at the distance from the boundary of the ball to the highest distance from the ball to a hyperplane or something.
So the worst A is not the zero matrix?
Maybe, I don't know. They have a concrete conjecture on what is. I think they have a conjecture on what C should be, but.
And this C is what comes from the zero A or not necessarily?
That I am not sure. A is, okay, so important, very good question. Important notice is that A is anything. This bound doesn't depend on A.
If I take A is a constant times the identity and then I let the constant go to infinity.
No, yeah.
So
sometimes it's zero.
Yeah.
But so you could have very bad condition number if A is very big.
no, but I'm talking about.
No, sorry.
I'm talking about the least singular value that I already. Very interesting point to discuss actually why it doesn't depend on A. For the least constant, well, I apologize again. This is the least singular value, not the condition number.
Yeah, the least because condition number does depend on A clearly.
I mean, you would believe that A equals zero is the worst, maybe, right? I mean, for other A's, it can be, the situation may be much better. If A is a huge multiple constant of the identities, then the probability is zero.
That is very good question to discuss because I have some other surprise later for this. Right? But yeah, but I put here the important noise exactly because I expect this reaction that it doesn't depend on A.
And for condition number, if your A is diagonal matrix with.
Of course, then you sigma 1 is big, then you can make anything. But here I talk about sigma n only. Sorry about the mistake. Okay. There is another kind of approach by me and Tao and also by Rutgers and von-Neumann that is also give you very good tellbound on this. And it is based on the so-called inverse Littlewood-Oxford theory and Terry and I have some version and Rutgers and von-Neumann later find a different version that also work. So it gives you uncomparable result. The result is better in some direction and worse in some other direction. Okay, but it is a nice result, so let me formalize it. Again, we take C, the random variable, to be normalized, and we put another assumption like it decay fast. So it decay faster than any polynomial. Okay, this is a technical thing that you may even improve on this, but let's assume that it decay fast. Doesn't need to decay as fast as the Gaussian, but something like that. Then you look at the least singular value. Then for any t, you have the same bound as in the Gaussian case of Shankar, Spielman and Teng. And you have 1 minus c to the n, which is necessary because you think of a random plus minus 1 matrix. It can be singular with probability half to the n. Right? So you do need this. And this also give, it reproves the Kahn-Komlos-Semeredi theorem. Of course, the reproof is, it is hard to tell because it uses the same technique that from Holland's paper that already have been used by Kahn-Kolot similarity. But it gives a quantitative, version of Kahn-Kolot similarity.
So this is true for any discrete Xi?
Yeah.
If it's discrete,
C plus minus 1, any discrete bounded C is okay. Yeah.
But the C may depend on
Exactly. The value of C is very small. The small c here can be 1 over a million or something. So it's not competitive in that sense. Yeah, but it gives you the right term here and the right order of magnitude of the probability estimate and give you the discrete case. So the theorem that Terry and I proved is that it can handle the case when you add the Spielman-Teng case. So this result actually the proof doesn't work if you add A to this. So the result when you need to add A to the matrix is something like this. And now the interesting thing is that the result will matter even if we talk about only the least singular value, but now we don't talk about Gaussian case anymore, we can talk about any case, then actually the norm of A will matter. So before, as Noga said, the norm of A doesn't matter, and actually maybe A equals 0 is the worst case. But in this theorem, and it is necessary, in this theorem, the norm of A does matter, and let me tell you the theorem. The theorem is that it gives you a Theobald. So, so if the norm of A is something like n to the gamma, then if you have the Theobald like this, then the right hand side is this. It is hard to think about anything. It's good to take a concrete example. Let me assume like if gamma is 0, gamma is half here, then actually this, or maybe half plus epsilon, then we know that the norm of mn is less than square root n, so this term is negligible. Right? And here we have half, so actually if you take the half here, you have n to the minus alpha plus half. Right? And here you have n to the minus alpha. So we got back the Rutgers-Verscheining's result with an extra, little over 1 arrow term. Right? But this theorem, it works for any A which can have polynomial or norm. Okay. Any question about this?
So the implied constants in the little o, they depend on the second moment or something?
No, little o, you can take them to be 1 over a million at the beginning.
So the actual value of the second moment doesn't matter here?
No. So the interesting thing is that, another important notice is that the bound, as I mentioned, the bound depends on the norm of A, which is different from the Gaussian case. But it's not only different, it is indeed necessary. So I can construct a matrix, a Bernoulli matrix, when you have the reverse inequality, like I can take norm of A to be L. Think of it as saying polynomial, say n to the 100 or something. Then actually we have, before we have lower bound, before we have upper bound on the right hand side, but now we have a lower bound. That doesn't go down with L. Right? So let me go back here and make a comparison. So here you see that the upper bound, right? Like this. And it involves the gamma, which is the norm of A. Now you see the lower bound. Right? And here it also involves the norm of A. And this surprised me, actually it surprised me quite a bit that for Bernoulli the norm of A seems to be played the role. We don't know that what happens. Clearly, A equal to 0 is not the worst case.
So can you choose an A so that with high probability it will be singular if you add the Bernoulli? With higher probability?
No. Yeah, we can make the distance to be very small, but not 0. And actually no, and the answer is actually definitely no, because the result of Kahn-Close similarity is still true if you shifted the mean of the matrix by something. It's still exponentially small. Yeah. So the question here is what's something I am very interested in is what is the right dependence on the norm of A. Right? So there's the gap between, if you look at these two theorems more carefully, there's a gap between the upper and the lower bound, and I don't know what the dependence is. Yeah, so that is, and it also tells you that smooth analysis is not always true if you talk about random discrete noise. And in the case that the core matrix can have very large norm, so you have problem there that you need to address. So there's just one line about why it has anything to do with the inverse Lillenwood-Oxford theory, is that it is something nice, and if you want something to take home, that's one line you can take home and forget about all the other things. That this the one line is that this something we call the second negative moment identity. It says the following. So you take your matrix and it have n rows, so it forms some parallelized pipette in Rn, and di is just the distance from xi to the opposite hyperplane. Right? So the thickness of the parallelized pipette in that direction. Then the sum of the di minus 2 equal the sum of the singular value minus 2. Equal, it's an identity. It's not an estimate. Okay? Yeah, so what you really have to do here is that, well, we want to control the sigma, and with some calculation you can see that actually the main term on the right hand side will come from the least singular value, right? So to consider the least singular value, you just have to compute this di, right? And to compute this di, you see that di is exact. If we have a norm vector v equal a1 up to an, then di is just the absolute value of the norm vector vi times the random vector xi. Right? It is a distance from this vector to the opposite hyperplane. It's a linear algebra. And then you can write it as a sum. Well, if vi is say a1 up to an, then it is sum of aj cj, right? When cj is c1 up to cn is the vector of coordinates of xi. J equal from 1 to n. So it is about a random sum, right? Random sum with the coefficient aj, and the inverse Littlewood theory gives us very detailed analysis of this random sum, and that helps you to understand it when it is large and when it is small. Okay, so now let me go to the second part of the talk.
So you use this Littlewood offer in the theorem?
Yes, in the proof of the theorem, the inverse, not the Lillenwood-Oxford, is an old theorem that but we recently developed something called the inverse of that, and that is very useful. Yeah, and also Ruth and Verschainin have a different formula, the different version of the inverse Lillenwood-Oxford that they also use in their proof.
All these DIs have the same distribution? All the DIs have the same distribution?
Oh, the DI. Yes.
Okay, so it's just computing one.
And and they seems to be large or small at the same time. That's not trivial, but it's true. Okay, so now I go to a different problem, back to the Edelman result, that when he compute the exact distribution for the Gaussian case. Okay. So the question here is that can you compute the exact distribution in general? Okay, what is the limit distribution after normalization by square root n, say? Or in other words, is Edelman's result can be extended for other distribution like Bernoulli, and clearly we see that's the trichotomy function that I don't know what it is about, but certainly not useful for Bernoulli matrices. And another motivation is the very specific conjecture by Spielman and Teng, again in their ICM paper. I think they make two conjectures. This is one of them. Is that yes, they want they take Mn Bernoulli, and so see that here is the n to the minus half normalization, and here is the factor that should came from just because of the discreteness, and what they want is that the main factor is exactly t. Well, we know that we can do c time capital C time t before, but what they do is exactly t. And Dan Spielman actually told me this long time ago, 6-7 years ago, and every time I met him, although he didn't go to my talk, he also forced me to go into his office when he can show me his experiment, because it's very easy to experiment, to make a numerical, and on the computer you see a straight line. Well, this is a straight line, right? And easily recognizable, like that x equal to y, and he say that it's 100% confident that this is the right answer. It looked nice and everything and so on. Although he didn't go to my talk.
So the conjecture is that it's equal.
What?
So the conjecture is that this is both upper and lower bound as a t.
He just make it for upper. Oh, they just make it for upper bound.
But the numerical evidence is that
The numerical evidence is that it gives you the straight line, and we will talk about that. Yeah. Still, he didn't go to my talk.
So what is the C again? The C.
Oh, C is something that should come in because we know that for a random plus minus 1 matrix, it can be singular with probability half to the n. So you need this. And t here can be even less than exponential.
What is C here? What is C?
Oh, for some value of C. So there,
Some values.
say 0.000001.
or just you want the equality for t that is not
Yeah.
extremely
Yeah, I think even for, so I think the main question, the gist of the problem is when t is something like polynomial, probably. Because if you go to t to be exponentially small, then actually this is the Kahn-Komlov-Semeridi type problem, which have a different flavor, I guess. We talk about the value, well, when we start to talk about the value of c, it's a different game, basically. Right?
Do you
Yes.
know what the best possible C should be?
Yes, I know. It is 1 minus c is, we know that the probability that Cn, oh, actually I don't know. What I know is that probability Cn is equal 0 is less than half to the half n. That's what I know.
But the conjecture is that,
Yeah.
that it's 1/2.
The conjecture is without this half. Yeah. There's other easier problem is that doing without this half. Yeah, so it seems that we need a new approach, and that is what I want to tell a little bit about is the projection method. Yeah, it has something to do. Well, not only is motivated by, of course, this guy, but it also has something to do with a general technique from computer science. Okay, which is testing, property testing. So property testing is something like this. Well, also in statistics we use a lot. You have a huge complex structure S, and we want to know some parameter of S. And the general philosophy is that quite often we have a good estimator for P by looking at only a randomly sample of S. Pick a few points and see what happens. And no guy here can talk for days about this. Or he can randomly sample parts of these days. It's still good, but okay, so here what is the last structure we want to talk about here? It's very important. I cannot compute, well, we talk about sigma n of Mn, which is of course sigma 1 of Mn inverse. And usually the sigma 1 is much easier than sigma n. At least in terms of. And it turns out that we can do the sampling technique to estimate the sigma 1 of this Mn inverse by just sampling a few rows and columns, the corresponding column. And that is the first step that was motivated by the property testing ideas. Okay. Yeah, so in the concrete form, if you want to bound this guy, probability that sigma n is small, it is the same as bounding probability that sigma 1 of the inverse is large. And there is a lemma that I found. Actually, it's only not even the result that Fritz, Kanan, and Van Baarle proved. It is only a subcase of this. It's very easy to reprove. That if you take a matrix, n by n matrix with rows, it's good to draw it here. And you samples, the few of them, say you sample, say like S of them. These are the sample one. And after sampling, then of course you have to normalize, because you're talking about only S columns here, and this guy have N columns. So you normalize by N over S. And then they prove that the difference between these two matrices is small, and small means that it is basically the sum of the length of the rows to the power of 4. Okay. That's something we just need to believe, and the proof is just by second moment method. It's take like one page. Okay, the proof is here and here, but I don't want to really go into it.
Can you show it again?
Yes. Yeah. So we look at the Frobius norm, the difference between the difference of these two guys. And we know that, and the relevance is that we know that this guy will actually upper bound the difference between the largest singular value.
Why is the sum of the fourth powers of why is that small?
I don't say why this. That is the hard technical part of the proof, but but at least this thing is easy to prove. Yeah. Well, of course, in the technical part of the proof, we have to show why the rho of the inverse of Mn is small, which is not entirely obvious.
But also, I mean, there's a question which maybe we're going to talk to the next slide or something. If you have a distribution of the entries of M, do you know anything about the M inverse?
Yeah, we know a little bit. We know enough to estimate this, but we don't know a lot. Actually, there's a question here I want to discuss. We don't know a lot. For instance, if I take plus minus 1 matrix, I invert it, so all the numbers will be rational number. Question is that how many digits you need to write down this rational number?
How many digits?
Yeah.
So you know the size by Edelman inequality.
Yeah, but after cancellation, after simplification, right? So if I have number like 12 over 9, that are 3 digits, but actually this thing is only let's say 4 over 3. Yeah. So I want them in the simplest form. Yeah, but I don't know anything about this. It is important for some application.
Sure.
Yeah.
It's certainly important for analyzing the running time of inverting algorithms. Exactly. Right?
Sure, but
To expect that there is a significant cancellation. I mean,
I don't expect. Yeah, I don't expect. There's actually I expect there's no cancellation. Yeah, but yeah. So thing about the inverse is quite tricky, but we know enough to estimate the RK. Yeah. Yeah. So the proof I will skip, as promised. Yeah. So the next step is of course to upper bound this guy. And there is a trick here that actually we have to upper bound them at the same time. You cannot, I cannot use the union bound and estimating one of them, but you have to make estimating the max of this guy, and because the probability bound is very small, it's n to the epsilon, n to the minus epsilon. So. Okay, so this talk will have a lot of hand waving. That unfortunately, so because the proof itself is like 40 pages, but I just want to give some of the main idea. Why the result will come from here? Yeah. So so why I call it the projection lemma, and how we go back from the inverse. Yeah, as I said, we know very little about the inverse matrix, but now we want to go back to the original one, and this is the core of the proof. Something called, it is simple lemma, but it is very useful. It is called the projection lemma. It says that if you take S-dimensional subspace, which is the orthogonal complement of the span of, say, n minus s columns. So you take so you take your big matrix here. You have n minus s column. So this column, this row will form an n minus s subspace somewhere, and now you take the orthogonal complement of this. So this is V. Yeah, so V will be orthogonal to x s plus 1 up to xn. And then you take the projection of x1 up to xz on this. And we have a set of vector, but now it will be VUS vector in Rs. This is S by S. And then this will give you the same, it will be the same as the vector, as the column of the matrix formed by the rows of the inverse matrix. So basically the identity here is that if you want to control the j singular value of the matrix B, which you get from the sample, the S by S sample before, it will be the S minus j plus 1 of the projection matrix. So the way it goes is, before we go from sigma 1 and sigma n to sigma 1 of m, right? And to estimate sigma 1 of m inverse, I go to the sigma 1 of B, which is the sample. And this technical projection lemma allow me now to go back to sigma s of C, which is the projection matrix. Right? So we go back from the least singular value to the least singular value. So before we go from the least singular value to the largest singular value, we do approximation by sampling, and then we do the projection to go back to the least singular value of the projection. Okay, so that is the logic of this. Okay, so and what I wrote here. Yeah, so now it reduces the problem of studying the least singular value of an n by n matrix to the studying of the least singular value of an S by S matrix. Okay. In the trivial case, you take S equal to n, then actually you do not gain anything, right? The projection is the matrix itself. And here's a key observation. If you take the orthogonal or projection on a small dimensional subspace, then actually the image of this projection will be close to Gaussian, no matter what kind of randomness you have originally. You take the projection of a Bernoulli vector, and you take a general subspace with small dimension in a sort of general position, then you will get the image of the Q will become liable. That's what I want to say. And that is the core. That's why we take S mode, and that works.
Why is the subspace you obtain by this procedure a general position?
Yeah, that is another key, technical lemma number 5, but something you need to prove. Yeah, and then to prove it, you need to use a Bernoulli lemma and so on and so forth. Yeah. So so that is that give you the sketch of the proof. Going back to the conjecture, we see, okay, here is what, again, the Spielman-Teng conjecture, but instead of 1 minus C, I want to confuse you and write it is SB, right? But it is the same conjecture as before. Now, the result I prove is that actually you take Cn, and I take S to be, say, n to the 1 over 100. Then actually the limiting distribution of Cn here will be the limiting distribution of Cs, but with Gaussian Gaussian entries. And then I just apply the Edelman result. So actually the result I prove is that Edelman result is universal. It only depends on the first and the second moment of the entries. And you need some tail bound, like the 100 moment should be bounded, should be bounded from above or something.
So the result for T is not only for Bernoulli, but
for anything, pretty much anything, yes.
Just understand this whole matrix inversion thing, presumably by invariance, for Gaussian entries, the inverse also will have Gaussian entries.
Is it true?
Because it's all going to be distribution is going to be orthogonal invariant, you know?
I'm not sure it's
I'm
true.
Sure
Actually, I'm certain it's not true. I think actually they are not even independent. The entries couldn't be independent. Okay, so what does it result? Tell us about Spielman-Teng. It tells us, what we just have to do is to take the result of Elderman and see what it does, right? And result of Edelman is give you this kind of distribution. So if you compute it out, it is not give you t, but it give you approximate t. It give you t minus t cubed over 3. And so it proves the upper bound because that is less than the upper bound. But it also tells you what the truth should be. This is something that the computer fools you. It's not the truth. And here that's why. If you take this line, these three lines are almost not, more or less cannot be separated, but one of them is y equal to x, one of them is y equal to x minus x cubed over 3. And one of them is for Gaussian, one of them is for Bernoulli, so there are 3 lines. And then they are more or less the same here. That's that. On the small scale, if we take about small t, then actually and if we delete 2 of the line, then we will bet money on it. It is a line x equal to y.
So you never did the experiment for big T? I mean, what about for t equals 1, for t equals 0? Because we think that
yeah, that for t equal to 1, then that's why they go with an upper bound rather than the truth. T equal to 1, then actually it will be strongly upper bound.
but you said something that you see a straight line.
Yeah, this 3 straight line actually, yeah, for small t. Yeah. Yeah, and this is something that you cannot guess. It's probably need the knowledge from the Gaussian case to make a guess for the Bernoulli case. Yeah, and so yeah, there's also some experiment. Yeah, so the theorem also hold for if we talk about joy distribution of not the least, not the bottom k singular value. So we want the joy distribution of the least and the next to least singular value, or the joy distribution even n to the epsilon singular value. Then we also have the universal theorem saying that the Gaussian assumption can be removed more or less, replacing by just a moment assumption. Okay, so yeah, so there's a lot of technical steps that I omit. I just want to mention one thing. Yeah, at the end is that there are a few other things I like to mention. At the end is there's the result of Feldham and Sodin. They handle the case when the matrix is not square. Say one of them is of size n, and the other dimension is of size 1 minus c times n. So they are, but c should be definitely larger than 0. And the techniques are very different. I don't know the technique enough to discuss it. And of course, these 2 questions are now the key question in the theory of random matrix. Is that we talk about not the extreme values, but the value inside the bulk of the spectrum and the symmetric case. So all of these have now been answered by a series of papers of Erdős, Yao, and co-authors, and also Tao and myself. But that is a very different topic. It is less combinatorics and computer science. So thank you very much.